Let us now look at an object that is going around in a circle, okay, circular path. And what we are going to look at is what is its angular position, okay. So suppose the particle was here and we want to know what is its angular position. We always measure angle from the x-axis and in the counterclockwise direction. So if it is counterclockwise, it will be called a positive angle. So let us say that this was 60 degrees. We would say the angular position, suppose I call this point A, the angular position of A is 60 degrees, but instead of using degrees, we'll use the radian measure. So 2 pi, you know, 180 degrees is pi, 2 pi is 360, so 60 would be pi by 3. So we'll say the angular position of A is pi by 3 radians, okay. But if instead of this being A, suppose the particle was here, suppose it started out here. Let us say that this was B. What is the angular position of B? And let me say that I am going this way 60 degrees. So I am going this way, right? From the x-axis, if you count, you are going in the clockwise direction. So anti-clockwise or counterclockwise, which basically means like this. And clockwise is basically like this. This is positive, this is negative, this is a convention. If you ask me why should that be positive, that's what everybody assumes. So if you're going in this direction, we're going to assume it to be positive. If you're going to go that way, we're going to assume it to be negative. So that means the angular position of B is going to be minus pi by 3 radians. Okay? Remember, the particle starts at B. It is a position. It is not the displacement. It is not moving anywhere. It is not moved from A to B. It is already at B. This fellow is already at A. But where is A? You have to start with something called the x-axis and you say, oh, A is 60 degrees or pi by 3 radians. So that is the angular position. Okay, so first point to understand is angular position is always measured from x-axis. This is a convention and it is measured in this direction as positive and that direction as negative. Now we always give the angle also in radians. Now when I am talking about this, look at this, there is an arrow that represents from the origin to, or the center to A, there is an arrow, right? Like this red arrow that you can see. This is called the radius vector. Well, it is the radius, but if I put an arrow there, this basically becomes radius vector. So what is the radius vector of the particle when it is at A? It is equal to RA. And so the radius vector, suppose it moves from A to, let us call this point, I've already used B, so let me say this was C. Then the radius vector has turned. The new radius vector is RC. Now, what is the angular displacement? So we'll now define this quantity called angular displacement, which is very different from linear displacement. Regular displacement means linear displacement. So what is angular displacement? However much angle has turned by, right? So how much has the angle turned by? So that's what I want to look at. So I need to come up with some number there. So let us say that this fellow made an angle of 30 degrees with the y-axis. So can I say that the angular position of C is the equivalent of 30 degrees? No, you have to always count it from here. So this is 30 plus 90, so it is 120. But we will write 120 in radians. Well, 60 was pi by 3, so this is 2 pi by 3 radians. But that is the angular position of C. What is the angular displacement when it goes from A to C? We write it like this. We say delta theta. Because there is no separate symbol. So angular displacement is written as delta theta from A to C. Sometimes I won't write the stuff below. I'll just write delta theta. How much is it? Well, that is the final angle, angular position minus the initial angular position. Right? What is the final angular position? 2 pi by 3 minus pi by 3. So this is 2 pi by 3 minus pi by 3 happens to be pi by 3. So this displacement is pi by 3. It is different from the position pi by 3. So if you say position pi by 3, it is at A. Displacement pi by 3 is from A to C. This angle is pi by 3. So we use the letter delta theta to talk about it. So delta theta, suppose I go from A to B. If I go from A to B, what is delta theta? This is A to B. I won't keep writing this next time. So we will say A to B and then we'll just write delta theta. How much is that? Final position, how much is that? Minus pi by 3 minus initial position of plus pi by 3. So delta theta is minus 2 pi by 3 radians. If I didn't mention radians, it's okay because radian measure you don't talk about. So if I go this way, does it make sense that it was minus 2 pi by 3? Yes, because you're turning this way. So if your angular displacement is like this, it is negative. If your angular displacement was like that, it would be positive. Instead of going from A to B like this, suppose I went from A to B like this. Then what would be the angular displacement? In linear displacement, if you go from A to B, however you go, your answer remains the same. Not so here. If I go like this, then I have to be very careful because my angular position has to be seen this way. Okay, so then B is no longer written as minus pi by 3. You will write angular position of B because you're going this way. You will say the angular position of B should be 2 pi minus pi by 3. So 2 pi minus pi by 3. Why? Because you're saying, oh, I started, imagine that I start there and come all the way like this. I start here and go like that, 2 pi minus pi by 3. That would be my position. We will see this in a minute, why this is important. So this is how much? 5 pi by 3. And so delta theta in that case, that is if you're going like that, would be 5 pi by 3 minus pi by 3, which is 4 pi by 3. Is that okay? So when you go like this, your angular displacement is positive. When you go like this, your angular displacement is negative. Okay, so that's something that generally we have to keep in mind. Generally, when we talk about angle, it doesn't matter if I say this is 60 degrees, I go like this once, 60 degrees. I make one full trip and come back. Where am I? I am at A. What is the angular position of A? 60 degrees. Ah, no. If you go and reach the same place 2 times, first time you reach, this fellow's angular position is pi by 3. This is A. If I go around and then again I reach A, now my angular position is not equal to pi by 3. What is it? It is 2 pi plus pi by 3. So it is 2 pi plus pi by 3. How much is that? 7 pi by 3. Wait a minute. How can I say that it has 2 different angular positions? It has. Why do we need this? Because otherwise, as you are moving, imagine that as I kept going from here, I kept going. My position was almost 2 pi. Then I cross over, my position becomes 0. That means my position suddenly changes, but I only moved a small amount. You expect that when you move a small amount, your position must also change. The value for the position must change by a small amount. You want it to be continuous. For it to be continuous, when you make one trip and you come back, it does not become 0. I know that in principle it is like 0 angle or like 1 degree or 2 degrees, right? But when you cross over, you don't reset it back to 0. You continue adding 2 pi. So you'll say 2 pi plus. So when will it become less? Well, if you went like this and now you're going backwards, then you start saying, okay, I'll subtract, because you have to go this much for you to get back to wherever you were, right? So if you go back in this direction, that means it will start to subtract. If you go like this, it will add. But remember that when you cross over, you will not get a sudden jump from 360 degrees to 0. 2 pi to 0. You will not do that. It will be 2 pi plus whatever extra that you move. That's why when this point goes around like this and comes back to A, you are back at the same position. Linear displacement is 0. But angular displacement is not 0. The angular displacement is 2 pi. If you made 2 rounds, angular displacement will become 4 pi. Okay? So I hope that is clear. Otherwise, there is a discontinuity. You had an angular displacement of, let us say, pi by 10, pi by 20, and right? 2 pi by 10, 5 pi by 10, and so on. and at some point you suddenly say that I have an angular displacement of 2 pi, then you have angular displacement of 0. That is a sudden jump. We don't like that sudden jump. We want it to be continuous. So if a particle moves continuously, we want the angular displacement and angular position representing it also to be continuous. So therefore, that is something that is important to do. So please keep that in mind, that when you cross over again, your angle increases. So it continues to add 2 pi plus. So 3 trips. If I made 1, 2, 3. Now I may be all in the same line, but this is not equal to 0 degrees. It is equal to 6 pi because 3 times 2 pi. Okay, just keep that idea in mind. So very simple and important principle. All angles are measured in radians. All of them, the convention is that this is positive direction. This is the negative direction, right? So if you're going anti-clockwise, positive, clockwise, negative. Second, the important, again, this is a convention, that the moment you cross over, you do not go back to saying that, oh, I reached A, so my angular position must be pi by 3. If you reach A after one turn, my angular position is pi by 3, where is that? Plus 2 pi, so therefore 7 pi by 3. Same point will therefore have multiple angular positions depending on how you reached it. Okay, so I hope all of these are quite clear. So once we start applying this to different kinds of questions, it should be straightforward. Remember that you need to convert everything to radians when you are solving problems. So now let us look at this question. So this question, there are 2 points, A and B, that are both in the first quadrant. That is important. A is here. The radius vector to A makes an angle of 45 degrees. So that means this is 45 degrees. This is A. And then the radius vector to B makes an angle of 30 with the y-axis. Now you can make it like this, you can have it that way, but it is in the first quadrant. So therefore, this is RB. This would be RB. And this angle is 30 degrees. Right? So we can directly end up saying that this angle must be 15 degrees. Because this is 45 and that is 45. Well, you can do it that way. And then you can say that this delta theta, which is what is asked, right? What is the angular displacement, is equivalent to 15 degrees. But you can't write 15 degrees. You have to convert it into radians. So how do we do it? 15 by 180 into pi. So this is going to be pi by 12 radians. 15 by 180 is 180 by 15 is 12. Okay, so we can do it directly. So this is one way to do this. But this is not really using any proper definition. You know, delta theta is the final angle minus initial angle. Because if I did it like this, whether I went this way or whether I went that way, it should be the same. Of course, you will see that you will get a minus sign because you know if it's going this way, 15 degrees plus. If you're going that way, it is minus 15 degrees. This is just a conversion. But suppose I wanted to do it like that. My final theta is this, right? But it is this angle, which is 60 degrees, which is how much? Pi by 3. I don't need to write radians. Initial angle is 45 degrees, which is pi by 4. Now you should keep in mind the following angles. So basically if you look at pi, pi is the same as 180 degrees. Pi by 2 is 90 degrees. Anytime you look at 90 degrees, you must think of pi by 2. Then when you look at 60 degrees, you must immediately think of pi by 3. And pi by 4 is 45 degrees. Okay, so if you look at pi by 6 is 30 degrees. Now usually you don't need pi by 12, but sometimes it's a good idea to keep in mind that pi by 12 is how much? It is going to be 15 degrees. But many times you do need to deal with 2 pi by 3, which is 120 degrees. Basically pi by 3 is 60 degrees. Keep that in mind. Pi is 180 degrees. But because this will keep coming up, I know you can always derive everything from here, but pi by 2 is 90, something that you will see almost everywhere. So you need it very, very critically. So it's something that is good to keep in mind. Pi by 4 is 45 degrees. Keep that also in mind. I mean, the rest of it you can always derive. Okay, so this is 45 degrees, pi by 4, 60 degrees, pi by 3. So delta theta is pi by 3 minus pi by 4, which is pi by 12 radians. If I had gone from B to A, then my displacement would have been minus pi by 12 radians. But since the question says the particle moves from A to B, it is this way. Now you can ask, why can't it go from A to B this way? It could. But we are generally talking about the shortest path from A to B. Okay, so we are saying that it's going to go from A to B in this direction. Okay, it's always in the first quadrant. So the question should actually say particle moves from A to B in the first quadrant, remaining in the first quadrant. Then of course the answer then becomes quite clear. So it's going this way. Okay, so this is the way we will calculate angular displacement.